Okay, in-person physics students, this is going to be a walkthrough of the calculations that you'll need to do for your lab portion of the exam with the spring load cannon. Okay? So what you're going to encounter is we're going to have a table or a bench or a stool, and we're going to place the cannon on that. And not only that, but the cannon will be placed at an angle. Okay, and so then we'll have when the cannonball is shot, we'll see this parabolic motion. Okay. It'll hit the ground. And we need to figure out where it's hitting the ground so we can place our target there. Now, a couple things that you'll be measuring in the lab. First will be the height. And when you measure this height, be very precise and careful and measure from the middle of the barrel. Okay, and so your height will be from the middle of the barrel down to the ground. Okay, so you'll have some height. And let's call that, let's give this a numerical value so we can work with that. So let's say that it's 2.300 meters. Okay. And then before this part, we're going to calculate muzzle velocity, and we'll do that with a horizontal component. Okay, and so you'll come into this portion of the lab knowing your muzzle velocity. Okay? And so that means this, you'll have some velocity initial. Okay, you'll have some velocity initial, and then you'll have an x and y component to that velocity. So let's do that off to the side here. So I'm just going to zoom in on this triangle. Okay, so I'm going to have some velocity initial that I will have figured out beforehand, and let's say that it's 5.200 meters per second. Okay, and we're going to have an x and y component on it. So we'll have velocity initial in the y direction and velocity initial in the x, and then we'll have some theta above horizontal. And the cannon has a little reader on the side that shows us what our angle is above horizontal. And let's say that it's 32 degrees, 32.00 degrees. I'm just going to work with 4 sig figs, and what I talk to my students about is we don't want to occur a rounding error in the middle of all of these calculations. So we're going to leave these big, long, full numbers until we get to the very end, and then that's when we'll do our rounding. Okay, so let's start here. Let's figure out the x and y component of this velocity using our trig skills. So if I'm looking at the y, it's opposite from our angle, and so the trig function we would use is sine, right? Because of SOHCAHTOA. Okay, so if I want to use the hypotenuse and the opposite, then I'm going to have to use sine. Okay, so without walking through it, each individual tiny step by step, because we've done that quite a bit, velocity initial in the y, we're going to take the hypotenuse, which is our initial velocity, and we're going to take the sine of theta. And so I'll plug that in my calculator. Make sure you're following along and plugging this into your calculator as well. It's important that you're feeling comfortable with that machine, right? That device that's going to help you. But if we plug something in wrong early on, then it's going to change our final answer. Okay, so I'm getting 2.75558. Okay, and I'm going to have my calculator store that like in the history, and so that I can go back up and grab that when I need it to. And notice I'm not limiting my sig figs yet. I'm waiting till the very, very end. And then velocity initial in the x would be the hypotenuse. That initial velocity, x, let me put squared there, it should be squared. And then it's multiplied by a cosine because we're adjacent to the angle. So then when I plug that in my calculator, okay, so so 5.2 times by the cosine of 32, 4.40985. Okay, and so now I've figured out our initial and final. Let's make our origin here at the base of the floor, so that'll be my 0, 0. And then this problem needs to be broken into 2 halves. Okay, so we need to figure out what's going on in the first half when we reach the apex, and then we want to figure out what's happening in the second half of the equation. Okay, so I want you to take a moment for the first half. That'll be the second. Okay, so we're going to deal with the first part and make your lists of knowns and unknowns. Here's your x, there's your y, lay out your x initial, y initial, all of that, and fill in as much as you can for this first part of the problem. Okay, so go ahead, hit pause, give that a go, and then I want you to come to play it again, and I'll get those filled in, and we'll compare lists. Okay, let's look at these lists. So, if I'm just focused on this first half, my cannonball starts right here, it ends right there. So my initial position as far as the x direction goes, I'm starting at the origin. I don't know this distance, and so x final, I'm not sure how far that's gone. Okay, and then velocity initial in the x, we solve for that. That is our 4.40985 number. Okay. The final velocity, well, let's think through this. Remember, a big key component of projectile motion is that the only force acting, or neglecting air resistance, the only force acting on the object as it flies through the air is gravity. Right? If I were to draw a free body diagram of this, it would just be force due to gravity. So there's no forces in the x direction to cause an acceleration. So the acceleration is 0. And if the acceleration is 0, that means we do not have a change in velocity. So what we're starting with is what we're ending with. We don't know the time component yet. Now to the y. The initial position, we're starting here, here's our origin. I am starting at some height away from my origin, right? I'm starting at 2.300 meters above my origin. I don't know what my y final is. I don't know what that height is, right? Velocity initial in the y, I calculated that. So that's 2.75558. I don't know the final velocity because there is an acceleration. There's a negative 9.81 meters per second squared acceleration. Oh, we do know the final velocity. I always seem to go back and remind myself. We're right here. We are at the apex of this parabolic motion. Okay? And so anytime we're right at the top of that parabola, for the briefest of moments, our velocity in the y direction is 0. Now if we take away the x part of this, see how the object goes up and then it comes back down, right? And so it's like if I took my pen and I threw it up, and then eventually it gets to the apex, it stops for the briefest of moments, and then it comes back down. And so in that moment, the velocity in the y direction is 0. The acceleration stays the same throughout. Okay, and then we have time, which we don't know yet. Okay, now here's what we need to do for the first half.
Artemis, could you come to the front office, please?
The first half of the problem, we need to figure out our missing information so that we can use it in the second half. Okay, so I want to figure out the time component, which will help me solve for y final and x final. Let's see where we at time-wise. Okay, so let's look, like we often do, let's figure out what the time is in the y, because we tend to get more information there. So I want to pick an equation that does not have y final, and when I look at my list, it's that third equation that we're used fairly often. So it'd be y final equals y initial plus velocity initial, and the y multiplied by time final, 1/2 acceleration, time final squared. And I'll get rid of my 0 components. And so that, yes, let's see, we have an initial, we have that, and we have time. Oh, we don't have the y final. We're going to use this equation in just a moment. We're going to use that to solve for y final once we figure out the time component. Okay, so let's pick an equation that has time but does not have y final. So I'm looking at my list of kinematics. So I do not want y final, and I do want a time component. And that first equation is really simple. That would be a good one to use. So we have y velocity final in the y equals velocity initial in the y, and then plus acceleration multiplied by time final. So that's 0. And let's get this page up. Let's subtract y initial. So we'll have a negative velocity initial in the y will equal acceleration multiplied by time final. I'm going to divide by that acceleration to solve for time. Okay, so I solved for that initial. So I'm going to go in the history of my calculator. I'm going to grab that number. Okay, so it's going to be negative of that number divided by negative 9.81. And so I get a time final of 0.280895. Okay. And again, I don't want to round in the middle of all my calculations, so I'm going to leave that big long number. It can go there as well. Okay. So we have the time component, and now we can use this equation to figure out y final. Okay? We have every bit of information now that we just plug in to figure out that y final. Nothing goes to 0. I take that initial of 2.3 and then I times it by the initial velocity, the 2.755 number, and I multiply it by the time component, the 2.2808, and then I'm going to add that to 1/2 times by the negative 9.81 acceleration multiplied by the time component there, squared. Okay. So I'm just going to plug all of that in. I'm going to show you as I do it. So y initial 2.3 plus the initial velocity, which is the 2.7, times by the time component plus, and sometimes, you shouldn't have to, but sometimes I like to put parentheses around this just just in case, just to remind my calculator we're keeping all of that together.